Last time we finished up on chapter 21, which is nuclear chemistry. So that leaves us just chapter 20 here to go. And chapter 20 is an organic chemistry. So we're really just going to kind of talk a little bit about organic chemistry, obviously, but more of a just kind of a little overview of it. We'll talk about a little bit of naming and stuff like that, maybe some reactions that occur. Um, Perhaps just kind of sets you up if you're off to organic after this class. You have an idea of some of the stuff that you'll maybe see as you go through it. All right, so let's get started. Let's start with the idea of organic chemistry, and probably the first sort of thing that you always see in an organic book is basically organic chemistry is the chemistry of carbon. It's basically, the chemistry of carbons and hydrogens. Um, the basic sort of connection of, most organic compounds are carbons attached to carbons, and attached to those carbons are hydrogens. So you have, carbons and hydrogens attached. And every so often, we kind of swap out some of the hydrogens for other elements, oxygens, maybe sulfurs, nitrogens, and we get some different types of organic sort of compounds. Organic chemicals are virtually in every sort of facet of our lives. A lot of products are organic, oils, petroleum, that type of stuff. It's really this long chains of organic molecules, carbons and hydrogens together. Things like acetic acid, for example, a weak acid is an organic compound. It's known as a carboxylic acid. Um, so we do see organic chemistry sort of pop up in a lot of places. Um, so there is a difference between sort of organic molecules and sort of inorganic molecules are things like say sodium chloride, which is an ionic compound. Something like sodium chloride is held together by very strong intramolecular forces, the electrostatic attractions. When we get something like butane, which is an organic molecule, that basically four carbons and all hydrogens that are attached, a very important part is they're actually held together by very weak intermolecular forces. So, because basically organic guys are made up of carbons and hydrogens, that's pretty much a non-polar bond. And because that's non-polar, usually a lot of organic molecules are non-polar overall. Some of them do have polar parts, but a lot of times what they'll use is a lot of dispersion forces as their intermolecular forces. So if you remember from Chem 50, dispersion forces are these weak, sort of temporary forces that are between one molecule and another. And that's what intermolecular forces are. They're the forces, right, that hold together one, say, water molecule with another water molecule, or say one butane molecule with another butane molecule. It's that force that holds one entire molecule together with another. And since dispersion forces are pretty much the weakest that you could get in terms of those, what we a lot see is a lot of organic compounds, or a lot of them are gases at room temperature. So if you think about some of the simplest organic molecules, things like methane, propane, butane, those are all sort of gases at room temperature. You take something like sodium chloride, which is held together by a very strong intramolecular force. And again, remember, intramolecular forces are always stronger than intermolecular forces. Um, we typically see sodium chloride as a solid under room temperatures, and super hard, and usually doesn't happen, not very flammable, can't really get it into the gas phase because of that really strong attractive force that holds it together. So all organic compounds, pretty much like I said, contain carbon and hydrogen. The carbon-carbon bond is the backbone. An important thing to remember about carbon, and that you learned hopefully with Lewis structures, is carbon pretty much wants to make four bonds in most cases. So it continuously will try to make bonds until it has four. It should never have more than four, which is a very common mistake people make in organic chemistry. They start drawing things and start double bonding, triple bonding. Before you know it, carbon's got like 32 bonds or something to it. So that's always good to keep in mind that, again, carbon has that four valence electrons. It wants to make 4 bonds, and in most organic compounds, it does achieve that by having sort of 4 bonds to it. And in most cases, if it's not carbon that's bound to another carbon, a lot of times the rest of the bonds could be hydrogen. Here's our simplest organic molecule you could have, which is methane on the bottom there, 1 carbon and basically 4 hydrogens. And again, everybody here, especially carbon, meets the octet rule. It's got 8 electrons around it. Hydrogen, right, which it meets the duet rule, only needs 2. And again, also, you should never have dots on hydrogen, right? It should only have basically 1 bond to it or 2 electrons. As we will see shortly as well, you may also recognize this geometry here. That is 4 electron pairs and also 4 bonds. That's your tetrahedral geometry, that 109.5 degrees. And that's also a very important sort of aspect of organic chemistry, is sort of the geometries that we see. This particular molecule is what's referred to as an alkane. And a lot of alkanes have that tetrahedral geometry. And that's why when you see, for example, as we will see shortly, one way you could represent sort of organic molecules is using line structure. And each of these sort of points here, I'll just draw them in circles here. Each of these guys are carbons, and assumed to attach to these carbons would obviously be hydrogens to give carbon 4 bonds. So this would have 1, 2, 3, 4, 5 carbons. This would be pentane, as we will see a little bit later. It typically has what is sometimes referred to as the zigzag shape, very commonly seen as you draw things sort of in line structures. And that really is because of the geometry here. Everybody's got sort of tetrahedral arrangement. It ends up giving it sort of that zigzag arrangement that we're very commonly seeing. Carbon, as I mentioned, will form single bonds, double bonds, and triple bonds with itself as well. And these actually give rise to sort of the first 3 types of organic sort of compounds that we see. Depending on certain features of organic compounds, we get different types of them, or different functional groups are sometimes referred to. So, really, functional groups in organic chemistry is really the part of the organic molecule which basically describes sort of what it is. And for example, here, this ethane is an alkane, and that's a group of organic molecules that basically have a functional group of carbon carbon single bonds. So, in an alkane, all the carbon carbon bonds are single bonds. We also have ethene, this is sometimes called ENE. And ethene is a group of organic molecules which are known as alkenes, ENE. And alkenes have a functional group of a carbon carbon double bond, as you can see here. So it has at least a carbon carbon double bond. And at the end here, we actually have what is also referred to as ethine, YNE. And this is a group of organic molecules which are known as alkynes, YNE. And these are guys that have carbon carbon triple bonds, as you can see here. So again, these are 3 sort of the basic sort of organic compounds. What makes them different is that functional group. So one has a single bond, one has a double bond, one has a triple bond. And you can actually see the effect on the name, as we'll get a little bit into naming as well. These are alkanes. This is what is known as ethane, ANE. This is an alkene, ENE. This is what is known as ethene, ENE. This is an alkyne, YNE. This is what is known as ethyne, which is YNE as well. So a lot of times the way we name different organic compounds based off of their functional group is very similar to the actual name of the functional group, or some part of that name sort of incorporates into it. As we will also see, alkanes are really important. They are pretty much the basis of everybody's name. So I think I hit the wrong button. There we go. So Very important, as we'll see, to remember sort of the first 10 alkane names. They essentially is how every single functional group pretty much gets their name from. As we'll talk about, you pretty much, when you go to name organic compounds, you really want to find the longest carbon chain, and that will match how many carbons there are in a certain alkane. And that's sort of the basis of all the names that will come after that. Again, as I mentioned here, methane, again, a major component of natural gas, like when you light a Bunsen burner or your stove. Ethene is a starting material in plastics. Um, Now, when we talk about organic compounds, some organic compounds are sometimes referred to as straight chains. And what that means is essentially it is just a straight run of carbons and hydrogens bound together. This also could be represented in line structure. It would look something like that. And again, this would be one carbon here, two carbons here, and three carbons here, which would represent one, two, and three carbons. Also assume that, as you can see up here, there are three hydrogens attached here. That gives that carbon four bonds. There would be two hydrogens here, gives that carbon four bonds, three hydrogens here, gives that carbon four bonds. So again, line structure, we typically don't put any of that in our stuff. It just kind of looks like that. This is also a ring type structure, also has three carbons, but it can also be represented in line structure, and it's sort of a triangle here. Again, one carbon here, two carbons here, and three carbons here, representing one, two, and three carbons. Again, each of these guys have a hydrogen basically coming off of it. This is an alkane. This is propane. Again, it all is carbon-carbon single bonds. And alkanes have a general formula of CnH2n plus 2. The N is the number of carbons. So in this case, for propane, we have three carbons. 3 times 2 is 6, plus 2 is 8 hydrogens we would have, which is what we see here. When we actually close up a straight chain into sort of a ring structure, we get what are referred to in this case, since it's all still single bonds. This is what is referred to as a cycloalkane. Cyclo meaning sort of a ring structure. Also, sort of a consequence of like closing, say, this side into this side, is if we just kind of connected them, those carbons at the end would have too many bonds. So remember, carbon could only have 4 bonds. So a consequence of sort of closing that is, or anytime sort of in organic chemistry, when you sort of make a bond, you oftentimes have to make room for it. And one way that we make room for it is we have to lose 2 hydrogens. So cycloalkanes have a general form of CnH2 times N. So in this case, we have 3 carbons. 3 times 2 is 6 hydrogens. Again, 1, 2, 3, 4, 5, 6. And again, that's just a result of when we kind of close it in on itself, we will have too many bonds if we just simply connect them. So we do kind of lose 2 hydrogens in that process that allows that ring to sort of close. By the way, these two sort of structures here, again, are a couple different ways that you can sort of represent organic chemistry. Again, as I mentioned before, this is oftentimes referred to as line structure. This is sometimes referred to as expanded structural formula. And that's sort of where you just kind of draw out everything, all the bonds, all the hydrogens are shown. That's sort of what is referred to as expanded structural formula. And another very common way that we can represent sort of these formulas, and I think we might have a slide coming up on it, is, for example, if we wanted to represent this guy, we could write CH3, CH2, and CH3. This is what is referred to as condensed formula. So those are 3 very sort of common ways that we could represent sort of organic compounds: condensed formula, expanded structural formula, kind of like a Lewis structure where you draw everything out, and line structure. If you go on to take organic chemistry, they think that's Chem 80 here. You probably will deal mostly with line structure, I'm assuming. That's usually sort of in majors chemistry, organic chemistry. That's sort of the formula that you use the most would probably be line structure, maybe condensed formula as well, but a lot of times line structure. Any questions on that so far? So, as I mentioned, organic chemistry and compounds are essentially that carbon-carbon bonds, carbon-hydrogen bonds, and that gives us a lot of different sort of classes of organic groups. But we get into even more as we really do start to sort of substitute out perhaps some of the hydrogens for other elements like nitrogen, oxygen, maybe a halogen along the way. And this gives us some other sort of functional groups in addition to whether or not we have, say, a single bond between carbon and oxygen, or a single bond or double bond between carbon and oxygen. These give us some other sort of functional groups. So here's some common sort of arrangement of some of these elements. Again, you can see hydrogen, kind of like what we talked about in Lewis structures. Obviously, it should only obviously have one bond, two total electrons. Carbon is the important one. Like I mentioned before, that is usually where a lot of people make a lot of mistakes. They get carried away, and before they know it, like I said, carbon ends up with a ton of bonds, more than four. Nitrogen, a lot of times, will look very much like ammonia. There's two sort of nitrogen containing functional groups in organic chemistry, and they both very much are similar to ammonia in that sense. Ammonia, again, is NH3, which looks like this. So there's sort of derivatives of ammonia, these common sort of nitrogen containing organic groups, amines and amides. Oxygen oftentimes will look like what we see there. Halogens as well. We'll oftentimes as well see some carbon oxygen double bonds is a very common sort of group that we see. Very common with this guy is like an OH type group, which we see in an alcohol. And then our fluorines oftentimes obviously will end up on the outside with a bond. And a lot of times, sometimes in organic chemistry, we don't necessarily include a lot of times in the pictures, or you'll see in a lot of times in the pictures, a lot of these sort of non-bonding electrons on things like the halogens and stuff like that. They are still there, but for sort of simplicity and not so much that the pictures get all crazy with dots everywhere. Sometimes in organic chemistry, these things are sort of left off occasionally, but they are still there. So here, for example, we see an OH bond, and this particular part of the molecule is another functional group. That's the functional group of an alcohol. And that's the OH group. And if you see that alcohol, that OH group, it's probably going to be an alcohol. And as I mentioned earlier, it is sort of based off of those alkane names. So here we have one carbon. If you remember, one carbon is methane. This is an alcohol, which ends in OL. So methane then becomes, as you can see there, methanol, OL at the end of it. And that would be the name of this, with this OH being the functional group. The appearance of this functional group does give it a different sort of property. We still have sort of a non-polar part of the molecule here. But this OH group is a polar bond. And that gives something like methanol some different properties than, say, an alkane that doesn't have an oxygen, that just has, say, carbons and hydrogens. The alcohol here can participate in hydrogen bonding because of that OH group, and it does make it fairly soluble in something like water. So as we sort of replace some of these hydrogens in these organic compounds with other sort of functional groups, sometimes we actually do gain some ability to do different things, like hydrogen bond, which would give it the ability to interact well with water, where something like a alkane that's all carbons and hydrogens would not react really well with water, again, because it's going to be using dispersion forces. Water wants to use hydrogen bonding. They're not going to be able to interact very well with each other. But here with that OH group, this guy can interact with water and become soluble in water. In addition, it also creates things like higher boiling points because something like methanol here has that ability to hydrogen bond with itself. What we see is the stronger those intermolecular forces, higher things like melting points and boiling points become. So we would expect something like methanol to have a higher boiling point than something, like say pentane or something like that, which is just all carbons and hydrogens. If we look at to the right here, this is formaldehyde. This is actually another different type of organic compound. The functional group here is actually the carbon oxygen double bond with the hydrogen. So you can pick whichever side you like here. Did you look at that? It's actually that part of it is the functional group for a type of organic molecule known as an aldehyde. And an aldehyde, um, also, if we think about sort of how many carbons we have here, we have one, which is again based off of methane. And sort of the formal name for this guy is methanal, Al. And that's because it's an aldehyde. So it ends in Al. And we, that's the common name is formaldehyde. So that's sort of its common name. And that's something you'll learn as well in organic chemistry. There's like three different names for the same molecule. And, one sort of a formal name, which is sometimes referred to as the IUPAC name. That stands for the International Union of Pure and Applied Chemistry. Those are the guys that come up with all the rules in terms of how you name things. So that's sort of like the official name, the IUPAC name. I'll write that down. I think it'll come up somewhere along the way here, but the IUPAC name. And then we have sort of historical names sometimes, and then we have sort of common names. So, for example, you know, uh, we have something like 2-propanol. 2-propanol is also known as isopropyl alcohol, and it's also known as rubbing alcohol. So that's all the same thing. Um, we have something like acetic acid, which is the same as ethanoic acid. So it's very common and sometimes very confusing in organic chemistry. Is there's a lot of sort of historical names that people still use in this day. There's also a lot of sort of common names, which again, obviously they're common, so it's very commonly used. And then there's sort of the formal name for a lot of things. So don't be surprised if you take organic, or if you take an organic, you probably know this already, that again, you could be looking at the same molecule and go, there's three different ways you could kind of give a name for that depending on sort of what you look at. Most of the time, most people, especially sort of in sort of organic classes and stuff like that, you usually a lot of times will go with the more, I'll say, formal name. The IUPAC way of naming it is usually the way that most people want to name these things. So when we draw these things, I sort of jumped the gun a little bit, but again, there's a few different ways that you could sort of represent sort of these guys. Again, sort of the expanded structural formula like we see here. Again, more structural formula, almost like a Lewis structure, really. Sometimes it's called expanded structural formula because of that. This is a condensed formula where we really, the difference is we really just don't draw out the hydrogen. So we kind of do CH3, CH2, and things of that nature. We sometimes have branch change. So sometimes organic molecules are not just straight across, they are sort of branched out and they have branches, kind of like trees. So if we look at something like this is sort of, if you want to think about like the main branch or the main part of the tree. And this kind of CH3 here is a branch group. And again, we can represent it obviously in our expanded. We could also represent it here in our condensed. And we could also represent it in line structure. This would be representing those three things as well. Again, just dissecting that for you. This is a carbon, which would represent this carbon. This is a carbon, which would represent this carbon. This is a carbon, which would represent this carbon. And that's a carbon, which would represent this carbon. And at the end of this line, there's nothing drawn. So that is also a carbon, which would represent this carbon as well. So again, as you could also see, We typically don't put the little circles in, we don't put the hydrogens in, but again, there is enough hydrogens at each of those carbons to get carbon to 4 bonds. So that's the importance of that carbon with 4 bonds. Obviously, not usually drawn in like I'm doing right now. Usually in line structure, just drawn like this. And again, it's assumed that you understand that basically there's hydrogens there, enough again to give that carbon 4 bonds. Question on that. And that's obviously line structure or line formula, is sometimes called. Sometimes, you get into some organic guys, which have a very long chain. And sometimes you get a lot of like repeated units that occur. So you have like CH2, 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 CH3. And sometimes people will do sort of shorthands that go, okay, I got 1, 2, 3, 4, 5, 6 sort of repeating units of CH2. So, they'll just kind of cut it down and go, hey, CH2, and there's 6 of them, and CH3, sort of a shorthand way of representing that kind of in a row repeated units. So if you come across that, it's important to remember that there are 6 carbons in here, and that this thing's not 3 carbons, but actually has 6 carbons, 7 and 8 total carbons as well. Sometimes in condensed formula, they'll starting to show it as well, like that, where you have this sort of group. Most of the time in condensed formula, people will probably sort of draw it like this. Um, and the reason for that, and the reason why you wouldn't want to perhaps write it like this, CH3, CH3, CH, CH2, CH3. Usually you wouldn't want to write it like this, because this would imply that sort of this carbon is attached to this carbon, that's attached to this carbon. And if that was the case, you then would have technically too many bonds to carbon. So usually you wouldn't necessarily draw it like this. Most of the time you'll kind of draw that guy up, so it indicates that, it's not really part of the main chain. It's sort of a branch that's coming off of the main chain. So that's usually a way that people will draw it. Skeletal structure, which is basically also another way of referring to line structures, is that sort of zigzag way, again, where it's sort of basically lines. Um, and again, with our cycloalkanes, this is cyclohexane. There are 6 carbons, which is hexane, and a ring structure gives us cyclohexane, which looks something like this. Again, as you can see over here, each of those carbons, which would be one here, one here, one here, 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 and here, each of those carbons again has 2 hydrogens attached to it. Now, if we have a group attached to some type of cycloalkane, we do typically just write out the group like we see here. This again is that OH group that we saw earlier, which makes this an alcohol. This has 1, 2, 3, 4, 5 carbons. 5 carbons is based off of pentane. It's in a ring, so this is cyclopentane, and it has an OH group, so this is what becomes cyclopentanol, OL, for our alcohol here, in terms of how we get to that name. And again, we'll get into some naming here a little bit later on as well. So, as I mentioned before, functional groups are really important in organic molecules. They basically tell you sort of what class of organic molecules you are dealing with. And depending on those functional groups that are there, you may end up with something that has some different properties than, say, the alkanes. You oftentimes can think of alkanes, those carbon-carbon single bonds, as sort of your basic units and of organic molecules, and everything sort of is based off of them. Everything's sort of built off of those alkanes, and again, by changing certain things, and it does give us different sort of functional groups. Another thing that you commonly will see in sort of organic chemistry is R. Um, R is just a carbon backbone, so sometimes generically people will say, hey, you have like ROH. R just means that's a bunch of carbons attached to each other. Could be one, could be two, could be all 30 of them, I suppose. And then obviously we have the functional group basically attached to it. So that's sort of a shorthand that you sometimes see. So some people go, what is the R? But so the R basically stands for sort of the carbon and hydrogen part of the molecule. And sometimes you'll see that. So let's talk a little about some of these, which we sort of did as earlier. Hydrocarbons. Hydrocarbons, much like the name implies, is basically all carbons and hydrogens in the organic molecule. If those hydrocarbons are alkanes, they all have carbon-carbon single bonds, as I mentioned earlier, as our functional group. And if they do, there were sometimes what is referred to as saturated hydrocarbons. Saturated hydrocarbons basically means that you have all carbon-carbon single bonds. The carbons have the maximum number of hydrogens that should be there. So, you know, if you have just this kind of simple guy here, this would be a saturated hydrocarbon. Again, they're all carbon-carbon single bonds, so this would also be an alkane. And basically what it means is each of these carbons have the maximum number of hydrogens that are available to them. Now, if your hydrocarbon is an alkene, as I mentioned before, it has that carbon-carbon double bond, and sort of a consequence of making that a carbon-carbon double bond is we do lose a couple of hydrogens. So as we talked about earlier, we lose a couple of hydrogens here. This guy does not have the maximum amount of hydrogens that it could have, and that is what is referred to as an unsaturated hydrocarbon. So as I mentioned before, alkanes have the general form of CnH2n plus 2. Alkenes, because they lose those two hydrogens, ends up with a general form of CnH2n. And what we get with alkynes, there's our carbon-carbon triple bond, also an unsaturated. And if you just look at that, if we made that guy a triple bond that we've been looking at, we end up with something like this. And again, to put that triple bond on, we essentially have lost two more hydrogens. And again, essentially every time you put on another bond, you're going to lose a couple of hydrogens. And that means that our alkynes have a general form of CnH2n minus 2 because of that. So those are three important sort of functional groups. Carbon-carbon single bond and alkanes, those are saturated hydrocarbons. Carbon-carbon double bond and alkenes, those are unsaturated because they have at least a double bond. And carbon-carbon triple bond and alkynes, also again unsaturated because they have obviously a double bond in that particular case. Another kind of class of organic compounds are aromatic compounds. And aromatic compounds contain the benzene ring. And the benzene ring you probably have seen before. It is this 6-carbon ring that looks something like this. It is not the cyclohexane one that we just saw because it actually has 3 double bonds in it. You could draw a resonance structure of it where the double bonds are on the other side. And sometimes, a lot of times, people will just draw the benzene ring with this little circle sort of in the middle. And that implies that those double bond electrons are moving around. So because they're delocalized, right, they're moving around the ring. So sometimes people sort of shorthand write the benzene ring as a kind of 6-membered ring with a circle in the middle, but it basically has 3 double bonds. And because it has the 3 double bonds, it basically has a formula of C6H6. Any questions on those there? So here's sort of a table of some of our functional groups. And again, you have a similar table, I think, in the book as well. But we have our alkanes, our single bonds, our double bonds, carbons, alkenes, alkynes, triple bonds, aromatic. Here are some other sort of functional groups that you'll see along the way. These are what are sometimes referred to as alkyl halides. And they're basically a carbon group that has a halogen attached to it. So, like your fluorine, chlorine, group 7 attached. Alkyl, because alkyl kind of means carbon group. Halide means halogen that has a charge, IDE, like you say bromide, fluoride, chloride. So that's what halide means. It's basically a halogen with a negative charge. We have our alcohols, as I mentioned earlier. The functional group is the OH group. An ether has the functional group of basically a carbon, oxygen, carbon sort of run. So you got this sort of functional group of it. An amine is our nitrogen containing group. And again, it is very similar to a ammonia. So it typically has sort of a NH2 sort of group attached. Again, very similar to ammonia, which is NH3. A thiol group has the SH group that is very similar to an alcohol, but it's a sulfur containing group. And that also gives rise to things like disulfide bonds and bridges that you see. For example, an amino acid cysteine has that group in it, and it's able to make some disulfide bonds happening between the two sort of SH groups in those different amino acids. A lot of functional groups will contain this group here, which is are part of this, which is an important thing in sort of organic chemistry. This is the carbonyl group, and a carbonyl group, and this is what is sometimes referred to as the carbonyl carbon as well. And it is basically the carbon oxygen double bond. This sort of part of the group is actually a polar group. So if we look at electronegativity, oxygen is more electronegative than carbon. So this provides sort of a polar part of a molecule between that sort of bond right there in that carbonyl group. There's a lot of sort of organic guys that have that sort of embedded in their functional group. And here are some examples of that. We saw earlier the aldehyde. So the aldehyde has the functional group of carbon, oxygen, double bond, and a hydrogen. Because of this group, and because it has a hydrogen at the end of it, it will always be at the end of the molecule. So this will always find itself at the end of the molecule. Because of that hydrogen, that functional group will always find it there. A ketone is another organic guy that has a carbon oxygen double bond, and that usually is a 3-carbon run. So you got at least a 3-carbon run, and in the middle you have the carbon oxygen double bond happening, and that is what is known as a ketone. So for example, just to kind of give you an idea, like we've been talking about in terms of names, we saw this guy just a second ago, which is our aldehyde with 1 carbon based off of methane. That's methanal. You could also do this guy here. You know, if you do, say, CH3, C double bond O, CH3. This is 3 carbons. 3 carbons is propane, the alkane name. Because it's a ketone, it actually ends in ONE. This is what is known as propanone, ONE, again, for the ketone part of it. So again, hopefully you can kind of see a little bit here, and we'll talk again a little bit more about it, I think, later on. Everything really does kind of come back to those alkane names, and you do sort of tweak the name a little bit depending on sort of the functional group that's there. And it's a lot of times named very similar to the functional group as well. Here's a couple more sort of carbonyl containing guys. We have our carboxylic acid here, and our carboxylic acid has that carbon oxygen double bond with the OH group here. This very often in formulas is written COOH. So if you see something written COOH, it's basically referring to this. So our good friend CH3COOH, that's acetic acid. And it basically is a carboxylic acid, a weak acid, as we've talked about many times here this semester. But this is really what we are talking about. This is really an organic molecule, major component there of vinegar. This is acetic acid. This is a carboxylic acid because it has that group. And again, as I was talking about, with different names, because this actually has two carbons. Two carbons is based off of ethane. And because this is a carboxylic acid, this is also known as ethanoic acid. Like carboxylic acid, ethanoic acid. So acetic acid, ethanoic acid, people sometimes just call it vinegar because it's kind of the main component of vinegar, all referring to the same guy here, which again is ultimately a carboxylic acid. An ester is very similar to a carboxylic acid. An ester has this sort of arrangement. It has the carbon oxygen double bond. It also has the oxygen, but instead of a hydrogen there at the end, it actually has another carbon. And that is because an ester is really made from the combination of a carboxylic acid plus an alcohol. And you basically take out water, and then you get your ester formed. This is a reaction which is known as an esterification reaction. Esters, a lot of esters are responsible for a lot of the smells, that we sort of associate things with, like pineapple smells and, oil wintergreen and that type of smell and stuff like that. So a lot of esters that you form through, say, a esterification reaction are responsible for a lot of sort of fragrances and stuff that we smell, say in foods and stuff like that, bananas and, all those type of smells and stuff like that. So, esters also, again, like I said, have this sort of carbonyl group and a slightly variation on this. And as you could probably start to see as well, a lot of organic molecules are really tied to each other. A lot of them are made by sort of putting two guys together, or maybe taking apart two guys, and you get two different types of organic compounds. So a lot of them are sort of based on that. Another type of carbon oxygen group that also contains a nitrogen is what's known as an amide, and that also is sort of based off a carboxylic acid. But so it has this carbon oxygen double bond, but instead of attaching to another oxygen, it's attached to almost an amine group. So it's got this sort of arrangement here, and this is our amide. And as I mentioned before, one way that you make an amide is kind of take a carboxylic acid and put it together with some type of ammonia type thing, or even an amine, which, if you remember, was that this type of group. And again, if you put it together, kind of take out water, you're left with this way. So if you kind of remove water, so there's a lot of reactions where we remove water and stuff like that to sort of make a lot of organic groups. And these are what are sometimes referred to as hydrolysis reactions, right? Just like we talked about hydrolysis reactions and earlier on with acids and bases. The idea here is a lot of times we will remove water or even add water. When we remove water, we're typically in organic chemistry pushing two things together. So a lot of times you remove water and kind of just push the remaining parts together, and you get a sort of organic group. And we could add water sometimes, and what that does is take an organic guy and basically break it back apart into sort of its components. So a lot of times water is used a lot in organic chemistry to either kind of put two things together if you remove it, or it's used to sort of break something apart into multiple things by adding it in. And so it's a very common sort of theme that you see in organic reactions. Any questions on those functional groups? So those different functional groups, like I said, will give you sort of a different type of organic compound depending on what you come across. So let's talk a little bit more in detail, I think, about alkanes and some other guys as well. Alkanes, as I mentioned before, are basically hydrocarbons. They have only carbon-carbon single bonds. And again, they should have carbon-hydrogen bonds. Alkanes that contain carbon in a no-ring structure are acyclic alkanes. And again, they have that general form of CnH2n plus 2. Acyclic alkanes are called saturated alkanes, Again, as I mentioned before, basically saturated alkane or saturated hydrocarbon basically means you have all carbon-carbon single bonds, and everybody has the maximum number of hydrogens that are present. Cycloalkanes, as I mentioned earlier as well, again, when you sort of close it up into a ring type structure, we do sacrifice a couple of hydrogens in that process, and it has that general formula CnH2n. It actually has the same formula as sort of our alkenes, again, because they made that extra bond and we lost a couple of hydrogens. A lot of cycloalkanes are definitely usually always exclusively written in line formula. So this is 6 carbons. This is cyclohexane, as it says. There's also sort of a 5 carbon guy, which is cyclopentane, all one word. We also have a 4 carbon guy, which is a square, if you want to call it. That is what is referred to as cyclobutane. And then your simplest sort of cycloalkane would be our triangle, which we saw earlier, which would be cyclopropane, which has 3 carbons. So definitely a lot of times cycloalkanes are written in line structure. And again, they're sort of these geometrical shapes, if you will. And that's usually how you represent it. As I mentioned, all alkanes will end in ane. And here are the first 5 alkanes, and it's really important to know these guys. Really the first 10, so we'll put them all together in just a second here, I think. So we have methane, which is basically 1 carbon, so we have CH4. We have ethane, which is 2 carbons, which means 2 times 2 is 4 plus 2 would be 6 hydrogens. We have propane, which is 3 carbons. 3 times 2 is 6 plus 2 is 8 hydrogens. We have butane, which is 4 carbons. 4 times 2 is 8 plus 2 is 10. We have pentane, 5 carbons. 5 times 2 is 10 plus 2 is 12. So these are the formulas. This is the structural kind of condensed formula over here, really. Why we have this, why don't we continue on? We also have, after that, we have hexane. Hexane is 6 carbons, and it would then have 14 hydrogens. We then have heptane, ane, 7 carbons, which means it should have 16 hydrogens. We would have octane, which is 8 carbons, which means it should have 18 hydrogens. We have nonane, which has 9 carbons and 20 hydrogens. And we have decane, which is 10 carbons and 22 hydrogens. So these first 10 alkanes, really important in terms of naming, not just alkanes, but pretty much everybody else. Everybody comes back to, these 10 names pretty much. You could represent, again, these guys in sort of line structure as well. So, that would be propane. That would be butane. That would be pentane. Again, typically this zigzag sort of approach. That would be hexane, right? And again, you could count the carbons: 1, 2, 3 propane, 1, 2, 3, 4 butane, 1, 2, 3, 4, 5 pentane, 1, 2, 3, 4, 5, 6 hexane. So again, that's how we very commonly represent these guys. So I would say super important. You should know these guys, right, and how to draw them. So a little bit about some of these. Methane, as I said, is your simplest, basically organic guy you could have. 1 carbon, 4 hydrogens. Again, has that 4 electron pairs and that 4 bonds, which is that tetrahedral arrangement. That is what gives it that zigzag sort of arrangement, not necessarily methane, but all these guys as they come together, because really they all have that tetrahedral arrangement. And that's why they're very commonly sort of drawn sort of in that zigzag shape. Ethane is our 2 carbons, again, 2 carbons and our 6 hydrogens that are attached there. Propane, 3 carbons and our 8 hydrogens. And again, you can start seeing that zigzag shape starting to form. In addition, a lot of our simplest alkanes are, as we mentioned earlier, gases like propane, methane, butane, all those type of things. These are 2 different representations of it. Sometimes people, when they see perhaps these 2 things drawn like this, they may think that they're actually different guys, but they're really not. So one important aspect when you go to name an organic compound is the basic thing that you want to figure out is what is the longest continuous carbon chain. So you're always looking for the longest continuous carbon chain. That doesn't necessarily mean that it is always the straightest. It could actually go straight, go up, go over, and all that kind of thing. The only thing that you can't do is you cannot kind of go back over. So you can't like go over, go up, come back down, go back around the same direction. So you have to kind of go one way until you kind of hit a dead end. So if we look at this in terms of carbons, we basically have 3 carbons straight across and 3 carbons, nothing else attached other than hydrogens is propane. And although the guy on the right may look different, if you just follow the path of the carbons, you got 1, 2, and then if you come down, you have 3. So this is ultimately still propane, even though it may appear different. They both would be named propane because the longest carbon chain here is 3 in a row, and there's nothing else attached, so they're both propane. Any questions on that? All right, here's butane. And again, we do see butane is basically 4 carbons in a row. Now, something different about what we were just talking about is these 2 guys here are not the same compound, even though they have the exact same sort of numbers of elements. If we count up everybody, this guy has 4 carbons, he's got 10 hydrogens. If you count the guy on the bottom, he's also got 4 carbons and 10 hydrogens. But they actually do have 2 different names. This guy here is, as we could see, 4 carbons straight in a row here. 1, 2, 3, 4, nothing else attached. This guy right here is what is known as butane, as it says. But if we look at the guy at the bottom and we count up how many carbons we have in a row, we have 1, 2, 3. That's a dead end, right? If we decided to go maybe a different direction, we have 1, 2, and 3, also a dead end at that point. So no matter sort of which way we go, the most carbons that we have sort of in a row is only 3 carbons in a row. So when you have an option like that, you might as well just take the straightest 3 to look at. So we'll take this straightest 3. Now, when we talk about 3 carbons in a row, 3 carbons in a row is not butane. It is actually propane. So the base of that second guy would be called propane because it has 3 carbons in a row. Now, if we look at it, though, we also have something else that's attached that is not part of the main group. We have basically this CH3 group that's there. That is not part of the main group or main chain. So this is sort of our main chain here, our 3 carbons in a row. What we have hanging off of there is actually a carbon that has 3 hydrogens. Right. So this carbon that has 3 hydrogens is also very similar to an alkane. And there's an alkane that has 1 carbon and 4 hydrogens. The 1 carbon of 4 hydrogens is known as methane. So this guy, which is referred to as a group, and this is sometimes referred to as an alkyl group, is missing one of those hydrogens. And the reason it's missing one of those hydrogens is it needs a way to be able to make this bond without giving the carbon there too many bonds to it. And what I mean by that is if I just took methane and tried to slap it into that carbon, this carbon will now have 5 bonds, too many bonds. So I can't just do that. So in order to make room for that group to attach, it actually has one less carbon. And believe it or not, these alkyl groups are named after the alkanes as well. So a 1 carbon group is not known as methane because it's missing a hydrogen. And because it's an alkyl group, this is what is referred to as a methyl group, YL. Very creative there, right? So that's a methyl group. So we actually have this methyl group attached. And in addition, in organic chemistry, you pretty much need to give locations of everything. So you have to give the location of where everything is. And the location of those groups in alkanes should always be the smallest number. And that means you basically have 2 ways you can number this. You could call this guy carbon 1, call this guy carbon 2, or this guy carbon 3. You could go the other way and call that guy carbon 1, this guy carbon 2, or this guy carbon 3. And it really doesn't matter which way you number it in this case. That group is attached at carbon number 2. So putting all those things together, the name of this guy that I've now scribbled all over is called 2-methyl propane. The 2 means that the methyl group is at carbon number 2. Propane is our longest carbon chain, and this is what is referred to as 2-methyl propane. Any questions on how we got to that name? So basically, when you want to name an alkane or most organic compounds, you want to figure out what is the longest continuous carbon chain. Again, doesn't have to be the straightest. Whatever that longest continuous carbon chain is, it will match an alkane name, and that will be the base of your name. You then want to figure out what is attached that is not part of that longest carbon chain. And those are groups. And those groups are also based off of the alkanes where you substituted out YL for the end of the name. You give the location. When we name something, we do a dash between a number and a letter, which is why we have the 2- methyl here, dash between number and a letter. And if you happen to have 2 numbers in a row, which can happen, we do a comma between 2 numbers. Any questions on sort of that? So because these 2 things are actually named something different, even though they have the exact same molecular formula, these are guys which are known as isomers, like we talked about in coordination chemistry. Isomers are guys that have the exact same molecular formula, but they have different connection. And that's why that these 2 guys are isomers. And that is why if we go to these 2 guys that we saw earlier, these are both propane. They are not isomers of each other. Even though they look different, they would have the same name. And that's really a good way to determine whether or not you're dealing with sort of the same thing or you're dealing with an isomer, is to name both of them. If you name both of them and you end up with 2 different names, they're probably going to be isomers of each other if they have the exact same molecular formula. If you name them both, even though they may look different and they both end up with the same name, they're not going to be isomers of each other. They're just something drawn differently. Any questions on that? There you go. So as I mentioned, isomers are basically the same molecular formula, but different connectivity. Constitutional isomers differ in the way they're connected. So again, if we just kind of count up everything we got going on in each of these, there's 2 carbons, there is 5 hydrogens and 1 oxygen on the guy on the left. Over on the right, there are 2 carbons. There is actually, I can't count. There are 6 hydrogens on the left. 6 hydrogens on the right, and 1 oxygen. They both have the exact same formula, molecular formula, but they have definitely different connectivities. The guy on the left here has the OH group, which, as we talked about, is an alcohol, and it obviously has a name known as ethanol. The guy on the right actually has the carbon, oxygen, carbon functional group, which is an ether. And this is dimethyl ether. And the way we get that name is you go to the oxygen, you find the group that's to the right. So as we just talked about, that's a CH3 group, which is a methyl group. You go to the left of the oxygen, you have another group, which is another methyl group. And since we have 2 methyl groups in the same compound, we use the prefix di. So dimethyl ether. They both have different names. They are both different organic guys, and they are isomers of each other. Any questions on that? Here's an example of some more isomers of pentane, or 5. So this again is 5 carbons in a row. Going to be pentane. This also has the exact same setup. But as I mentioned before, what we would want to look at here is longest continuous carbon chain. In this case, 1, 2, 3, 4 carbons if we went this way. If we went the other way, 1, 2, and we went up, that is 3 carbons. If we went right to left, 1, 2, 3, and 4. So there's a couple of different ways you could actually get 4 carbons in a row, but it does look like 4 is the longest continuous carbon chain. So usually easier just to kind of take the straightest. So remember that 4 carbons in a row is butane, which is where the butane part of it comes from. Then attached to that main chain is we have one group attached. This is a 1 carbon group, which is a methyl group, which is where this name comes from. And we need to give the location of that group. And we could number left to right, which would be 1, 2, 3, 4. We could have also numbered right to left, which would be this is carbon 1, this is carbon 2, that's carbon 3, and that's carbon 4. Whenever we name something in organic chemistry, we want to give either the functional group, we want to give the groups that are attached, always the smallest number. So you're always going for the smallest number. And that is why we would, if we were to name this guy, number it this way, because going in this direction gives our methyl group the smaller number, which is 2. And that's how we get to 2-methyl butane as the name of this guy. Again, different name than this guy, which means they are isomers of each other. If we go to the very last guy, longest carbon chain, we have 3 in a row. If we go just straight across, we also have 3 in a row. If we go this way and up, or if we went, this way and up as well, we would have 3. And lastly, if you went, just this way, oddly, as it may seem, you have 3 in a row. So no matter what option you got, and you always kind of want to look for all your different options just to make sure, because sometimes you might miss one. We might as well just take the straightest. So if we just go straight, that is 3 carbons. 3 carbons is based off of propane, which is where the base of the name comes from. Now, in this particular case, we have a CH3 group up on top, and that is a methyl group. We also then have another CH3 group that's not part of the main chain, also a methyl group. That again is 2 methyl groups in the same molecule. It doesn't have to be at the same carbon, but in the same molecule, and that is what is referred to as dimethyl. Now, in organic chemistry, as I mentioned, we do need to give the location of everything. If we were to number the 2 ways we can number the main chain, 1, 2, and 3, or we could go the opposite way, 1, 2, and 3. In this particular case, it does not matter. Both of these groups are located at carbon 2. And that is where the 2 comma 2 comes from. 2 comma 2, because that is two numbers next to each other, dash a letter, as we see here. And that is sort of our name. So 2 comma 2 dimethyl propane, also a different name than the other two. These are all three um, isomers of each other. They all three have the exact same molecular formula. If you counted up everybody, you should end up with 5 carbons and 12 hydrogens. Any questions on any of that stuff there? Here's the rest of our first 10 alkanes. And again, super important to sort of know those, and definitely makes life easier as you go through different organic molecules, as everything, as you could hopefully start seeing, is really based off of these kind of 10 names, a lot of it. So as I mentioned before, sort of the the formal way of naming something is the IUPAC way, and that's the International Union of Pure Applied Chemistry. And again, so a lot of times in organic chemistry, they'll say, hey, give the IUPAC name. And that's sort of the official way of naming that particular organic compound. And it really is based on the type of organic compound you got dealing with as to how you would name it. So let's just talk about some of these rules. We sort of jumped the gun here about sort of how we name it. So just to kind of reiterate some of the main points that we just did there, really to get sort of the base of the name, I call it the kind of root of the name, is you want to always look for the longest continuous carbon chain. And usually you want to look for the longest continuous carbon chain that contains the functional group. So in an alkane, the functional group really is the carbon-carbon single bonds. But if you got to an alkene, for example, the functional group would be a carbon-carbon double bond. So you would want the longest carbon chain that contains the carbon-carbon double bond, for example. If you got to an alcohol, it would have an OH group on it. You would want the longest continuous carbon chain that contained the OH group. So when we name things in organic chemistry, it's always the longest continuous carbon chain, and usually it should contain the functional group. Once you figure out what that is, in probably most cases, it will match one of those 10 alkane names, and that will be the basis of your name. The next thing that you really want to do is figure out, what type of groups are attached that are not part of that longest continuous chain. So as we kind of mentioned a little bit earlier, we oftentimes will get some alkyl groups, and they are really based off of those alkanes. The difference is they are missing a hydrogen to allow them to connect in. And by missing that hydrogen, they're no longer an alkane. They become what is referred to as an alkyl group. But they are named very similar to our alkanes, again, dropping the last part of it and putting YL at the end of it for the name. Now, we can have one sort of hydrogen removed. So as we can see here, our methane without a hydrogen is CH3, and that is our methyl group. If we remove a hydrogen from ethane, it becomes an ethyl group. If we remove a hydrogen from a propane, it becomes a propyl group. So we can get some different groups attached that have some special names, and it depends on what hydrogen is sort of removed. So to talk about that, we should probably talk first about classifying carbons. Carbons can be classified as primary carbons. And that basically is a carbon that's attached, surprisingly, to one other carbon. There are secondary carbons. And secondary carbons, kind of like the name implies, is a carbon that's attached directly to two other carbons. And there are tertiary carbons, which is a carbon attached to three other carbons, 1, 2, and 3. So we can classify carbons as a primary carbon, which again means it is directly attached to one other carbon. a secondary carbon, which means that carbon that you're looking at is directly attached to two other carbons, and a tertiary carbon, which again means, as the name implies, that that carbon is attached to three other carbons. So what does that have to do with groups? Well, if we look at, for example, propane, which is this guy, if we draw out propane, if we were to identify the carbons in these guys, in propane, as either primary, secondary, or tertiary, this carbon right here is directly attached to only one other carbon, the carbon in the middle. This is a primary carbon. If we do the guy on the other end, that carbon right there is attached to only one other carbon, the center carbon. And this guy would also be a primary carbon. I'll put it in a box. The guy in the middle in the box is actually attached to two carbons, a carbon on the right and a carbon on the left. This is what is referred to as a secondary carbon. Any questions on how to identify that there? Okay. So what does this have to do with groups? Well, if I remove a hydrogen from the guy at the end, the carbon at that end, or the carbon at that end, I end up with a group that looks like this. Where this group would attach to the next carbon as a group would be at the end. And this would be a propyl group, sometimes referred to as N-propyl group, but N for normal, like a propyl group. And I would also get the same guy if I took off the hydrogen on the left-hand side as well. It would just be the same thing. But if I took off a hydrogen on my secondary carbon, I would actually end up with a group that looks something like this. Where the connection point for this group would actually be on the secondary carbon. This actually has a different name. So this is what is known as the isopropyl group. So this is isopropyl group. So even though they are the same group, they have the same three carbons and what we got there, 7 hydrogens. Because of where the connectivity point is in this particular case, it actually gives us a different name for this group. And this is sort of a historical name known as isopropyl. By the way, if you pop in there if you pop in there a OH group, that is how we get something called isopropyl alcohol, right? That is where that name comes from. This is isopropyl group. By the way, that's also what I talked about earlier. This is also known as 2-propanol. Again, because it has 3 carbons, which is propane, has an OH group, which is an alcohol, and that OH group is on carbon number 2. So that is 2-propanol, isopropyl alcohol. But this is an isopropyl group as a result of removing a hydrogen from a secondary carbon versus a primary carbon. So you do get some different sort of groups. All these that we see in this table are all sort of removal of the hydrogen from sort of the end, a primary carbon, and we get sort of a normal group. So you will see some different sort of names of certain groups depending on sort of what hydrogen or it came off of, or guess what carbon the hydrogen came off of. And here's some of those examples here. Here's isopropyl, which I just talked about, oftentimes, sort of abbreviated like this. Again, connection happening here on our secondary carbon. This is isobutyl, also very similar, CH3, CH, CH3, and a CH3 there with our group here. This is sec-butyl, sec-butyl being, again, 1, 2, 3, 4 carbons in a row, which is based off of butane, which is where the butyl part. Sec means secondary. So the connection point is at the secondary carbon. Again, that carbon I just circled attached to 1 carbon there and 2 carbons there is the secondary carbon. T-butyl or tert-butyl, tert for tertiary, butyl for butane, 4 carbons in this guy, and the attachment point is at that tertiary carbon as to where the attachment point is. So there's a number of sort of groups that have special names based on sort of where that group will attach. Any questions on that? Okay, so to name these guys, we sort of talked about a couple other things. If you have more than one group, the same group in the molecule, we do use prefixes like di, tri, tetra to indicate that there's 2, 3, or 4 of those groups, like we saw with dimethyl. We do want to name, in terms of alkanes, the groups in alphabetical order, regardless of number, and prefix. So regardless of number and prefix, we go alphabetical order. And we want to number the longest chain, whichever way gives the groups and alkanes the smaller numbers. So again, looking at this guy here, longest carbon chain, they boxed it for us. It is 6 carbons, which means the base of our name is going to be hexane. We have 1 group attached here, which would be a methyl group. And again, we can number this chain 1, 2, 3, 4, 5, 6, or we could go 1, 2, 3, 4, 5, and 6. Going left to right will give this group the smaller number. So this would be 2-methyl hexane in terms of the name. Again, in line structure, will look something like this. So again, in line structure, you do the same thing. You'd go 1, 2, 3, 4, 5, and 6. Or you could go 1, 2, 3, 4, 5, and go up to get 6. But no matter which way you go, it's going to be 6. So again, this would be our longest continuous chain, which would be hexane. If you have a line and nothing written at the end, again, that is a carbon, and that really is a methyl group, right? So carbon should have 3 hydrogens in that case, and that's where our methyl would come from in line structure. And again, you would number it the same sort of fashion to 2. So, you want to follow the sort of those rules. Any questions on that one? So like I said, longest carbon chain, doesn't matter if it's the straightest. You do want to kind of choose all of your options and figure out what is the longest. And again, the only real rule is you can't backtrack. So if you start going this way and you go up and you go over, you can't hit a dead end and decide I want to go back, down, and around. You keep going in one direction, whichever it leads you, until basically you hit a dead end for your longest continuous carbon chain. As you can see here, kind of the straightest. Again, if it came down, it would be here, could go down and then up. And again, you usually want to kind of try all your options to see what you end up with. And again, that's what we talked about. Lowest number, substituents in their order, longest continuous carbon chain. Again, as I mentioned before, if you happen to have more than one prefix, more than one of those groups in there, we do use those prefixes di, tri, and tetra, like we talked about earlier there. And again, lowest numbers. So in this case, we do have 2 methyl groups attached. They boxed our longest carbon chain. So this is 1, 2, 3, 4, 5, 6. So again, the base of this name would be hexane. We have 2 methyl groups. So again, dimethyl, because there are 2 methyl groups, does not have to be on the same carbon, but in the same compound. And a numbering, we could go 1, 2, 3, 4, 5, 6, or we could go 1, 2, 3, 4, 5, 6. Going left to right, we have a groups at 2 and 3. If we went right to left, our groups would be at 4 and 5. It is as simple as 2 is smaller than 4, so we would not want to go this way. So by going left to right, it does give our groups the smallest number, and we do need to include both of them. So 2, again, comma between two numbers, 3, a dash between a number and a letter, and this would be 2,3-dimethyl hexane. Any questions on that name there? And again, in terms of sort of line structure, what it would look like, it would look something like this. So this is the same thing here. Again, why is it 3? So it's 3 because, again, we'll do it on the line one so we can see it. So our longest carbon chain would be 1, 2, 3, 4, 5, and 6. So that's where the hexane part of it comes from. Now, we have then two groups, one here and one here, and they're both basically lines, right? So in line structure, if we just have a line, at the end of it, it's assumed a carbon. And again, remember the carbon needs to get to 4 bonds. So it's basically a CH3 group, which is a methyl group. So each of these kind of blue guys, which are represented here, they're methyl groups. So that's dimethyl. So the last thing that you want to do is number the carbon. So this would be carbon 1, 2, 3, 4, 5, and 6. If I numbered left to right, and numbering left to right, so we'll go left to right, the two groups end up at carbon number 2 and carbon number 3. Your other option to number the longest carbon chain would be going right to left, which would be 1, 2, 3, 4, 5, and 6. If I went right to left in terms of my numbering option, the group would end up at carbon number 4 and carbon number 5. So we're looking for the smallest numbers. So because 2 is smaller than 4, we would not want to number the way that gave us that, which would be this way. We don't want to go this way. We would want to go the other way because it did give us the smallest number in terms of the location. And that is where we could find each of those methyl groups. So the 2 means that if you go to carbon number 2 on that chain, you will see a methyl group. If you go to 3, it also tells you you will find a methyl group at carbon number 3. And that's how we get to 2,3-dimethyl hexane. Question on that? You're welcome. All right, so hey, we're getting into this. What do you think? All right, we'll lay it up here for lecture. We'll take a little break here, stretch our feet, and we're having so much fun. We'll continue on talking about organic. I think the lab is technically some more of this, so you'll get some more practice and stuff like that. But we'll finish lecturing. I think the rest of it, we'll also talk about, again, what you'll need to do for that last lab, which is the organic one. And then we'll talk about the finals next week and all that good stuff. So why don't we take a break right now, get up, stretch, and we'll